I would have been sad. Yeah. Sure said. Thank you. Okay. Big thank you to Caitlin Kisling for making sure I start the video. All right. So we're going to look at those two variables, mass and volume, and their effect on density. One thing that I want to just make sure I cover clearly, because as the day goes on, I think of different things. And so when we talked about the milligram, the kilogram, like the big version and the small version, so we said that this is like our kilogram of our kilogram, right? And then one of these single grams, let's move this over, thank you. One of these M&Ms was like a single gram, okay? And so if I would take 1,000 of these M&Ms, which is what's in this bag, that's how I get my kilogram, because kilo means 1,000. That'd be the big version of the gram. If I wanted the small version, I could take a single M&M and I could chop it into 1,000 equal pieces, which would be about the same size as like a single grain of salt, which is a milligram. But if this M&M, if I could chop it evenly, which would be pretty hard to do, but if you could, then 1,000 of a single M&M would be that milligram. So obviously that's dealing with a really small portion. I think that your notes are in the binder from yesterday, if you want to grab them out of the blue binder. So that is kind of one thing I wanted to talk about. Another thing, just so you have that good visual of what's going on, this is how we represent a liter, right? This is a 1 liter bottle. So it would take 1,000 of these to make a kiloliter. And so the average comparison is like, it would take 1,000 of these to fill 4 standard bathtubs. So like a regular old bathtub, not a big fancy jacuzzi one or anything like that, but just a regular old tub, 1,000 of these, so like 250 in one, 250 in another, 250, 250. So that's a lot of water bottles to make that 1,000 kilograms. Okay, or that 1,000 liters, right? So our kiloliter. If I wanted to talk about the small version of this liter, again, this would be like chopping this into 1,000 equal pieces, and that would be like our milli, because milli means 1,000. So milli is small, kilo is large, so we can make our liter big or small, and we can also make our M&M, our single gram, big or small as well. Okay, so I just wanted to kind of go over that again really quickly. Okay, so that gets us to using density of water. Water has a known set density, and it's actually a pretty easy one to remember. And so we use water for a lot of comparisons, all right? So if something is going to float, it's going to be less dense than water. If it's going to sink, then it will be more dense than water. So water is a really good, handy tool to figure out if things float or sink. That's easy to see, and then we know if they're more dense or less dense. So this is slide 13. And so water's known density is 1 gram per milliliter. Again, notice how I am capitalizing the L for liter.
These slides are a little different this time. You can find the number right there in the corners. Okay, so you're going to keep track of where you're at.
And so in this state, is water a liquid or a solid? How do you know? Besides the picture. Huh?
Splashes around.
Okay, but if I don't see that picture at all, how do I know, Kate?
It takes the shape of whatever container it's in.
But I can't see the shape of the container. There is something else that gives it away.
Vegetables are funny.
No.
Nope, you're not seeing this picture. It's not there. What do you think?
The milliliter.
The milliliter, right? Remember, L, the liter means liquid. Now, if this was dealing with solid water, like ice, anybody know what those units would be? Nope. The gram would be talking about mass. We're still talking volume. No. Maybe look over there on the board. I tried to put some helpful things in that corner for you. Centimeter cubed. Cubed, right? Because it's in 3 dimensions. So over here, I'm going to try to keep track of some important things that might be helpful for you. So like if you get stuck and you're like, oh my gosh, I don't don't know, maybe just look up there, like, sometimes, like, there's some helpful things. So the 1 milliliter equaling the 1 centimeter cube is written up there, so good. This is gonna be a common question that I'm gonna keep asking you. How do you know, is this a solid or is this a liquid? Okay, all right, and it all comes back, if you see the L, the milliliter, the kiloliter, just the liter, anything with the L for liter, you know liquid, okay? Okay, so this number, this 1 gram per milliliter, is a constant that we can use to find the relative density of other objects. So when we talk about relative density, what we mean is, do you remember when we did the dating of the rock layers? And so we didn't know like exactly how old something was, but if you had something down here, it was older than something up here because of that law of superposition. It was called relative dating. Not like you're dating your cousin, you're from Alabama. That's rude. Maybe some of you are from Alabama. I don't know. Just making it up. I don't want to offend anybody. But it's not talking about dating your cousin or anything like that. When we talk about relative dating, it's that comparison, right? So this is the same idea. This is using a comparison. So this is more dense than this, or this is less dense than this. And so you might not even know the exact densities, but you could place them in order. This is the least dense, this is the most, and kind of like go on up based on what you see, in the diagram, the picture, or whatever it is you're looking at. So here's the key. If an object floats, it's going to have a density of less than 1. Density of water is 1, so less than 1 means it floats. So from this picture, now you're allowed to look at the picture, what are some things that are less dense than water that you see here? Give me one, Cole. An orange. I wouldn't have thought that, right? I would have thought an orange would sink, but it doesn't. What else? Charles, what do you see there?
Tomatoes.
Yeah, it's either a tomato or an apple. It's hard to tell. One of the two. It's hard to tell. Yeah, we'll go with the red. Tomato or apple. What else? Kayla? What was it? Yeah, like that cork. It looks like a cork from maybe like a wine bottle, possibly. What else? What do you see, Austin?
The green pepper.
Yeah, a big green pepper. And so it's like halfway above the water, so it's probably even less dense than maybe the orange or what's this yellow one?
Lemon.
Lemon, probably, it looks like. It could be a pear, but yeah, the lemon. And then that looks, I don't know if that's a grape or an olive. It's kind of hard to tell. So what are some things that look more dense than water? The potato, and then a carrot, right? Again, I'm not sure if this is an olive or a grape.
That's a good
One is each. That one looks more like a grape. That looks maybe more like the olive. You think so, Charles? You're getting a good look. Okay. All right. So if an object sinks, then it has a density that is greater than 1. That's pretty logical, right? Kind of makes sense. Kind of like, okay, not too confusing, hopefully. So we have all these things at the top that are less dense, so they have a density that is smaller than 1. So like anything 0.9999999 as their density would be obviously matching any of these items here. Anything that is like anything higher than 1.0 would be our densities down below. All right, so this could even happen with liquids, right? So here you have, it looks like a 3 different liquids, but then you also have some solids that are in there as well. So this is kind of cool. So you can see like this looks like a nut from like you would put on a bolt. There's something there. I can't really tell what that is. Again, not sure exactly what this is. But even without knowing what they are, where is the most dense item going to be? Is it going to be at the bottom or the top? Raise your hand if you think the most dense will be at the top. Raise your hand if you think the most dense will be at the bottom. Okay, so if we go most dense, and then we kind of work our way up, then the least dense is going to be at the top. So we're always like working on stuff and get like dirty and grimy, and so my husband likes to have like a thing of dish soap in the shower, and like he'll use it to get like extra oil and grease. Like he gets the big stuff off outside, but then like if like he really has to scrub, like so he'll have dish soap in the house. or in the shower. And so I had a bottle, and I can't remember which way it went. Like one time, like I can't remember if it was the Dawn that I had and I was refilling it with palm olive, or if it was vice versa. But I had two different dish soaps, and his bottle was just about out. But I didn't want to switch the bottle till it was out, so I was like, okay, I will just take this little bit that's left and put it in my other half bottle that I had filled, like my dispenser and my sink in my kitchen. And so I had half a bottle, and then I had one that had just a little bit in. So I took the Blue Dawn and I put it into the palm olive that was half full. And so I'm squeezing the Dawn, and I just thought, it would stay there at the top because that's where it's landing. Well, it flipped, and all the blue went to the bottom, and the orange palm olive went to the top, because they are different densities. And you wouldn't think it, but it gets, it's separated out. And so I had like a perfect, and it looked pretty much like this, where you had like the one color on the bottom and the other color on the top. And I could be flipping it. I can't remember which one was more dense, if it was the Dawn or the palm olive, but whichever one, I had the least dense one in, and I added the more dense, so the more dense flipped and went to the bottom. So I do have a bunch of Dawn soap right now, so I might try to do this with you guys if I can remember to get some palm olive. And it's pretty cool, because like you wouldn't think like, okay, it's at the top, it's just gonna stay at the top. And it actually, like I watched it totally flip, so it was pretty cool. Give me 1 second. Okay, sorry. Have lots of different things going on today, so thanks for letting me take care of that. Okay, so let's move on. I told you that before we get to the labs, where you're gonna actually have to measure mass and measure volume, we'll do a review with the cheat sheets for triple beam balances and graduated cylinders. But we're just gonna kind of go over this real quickly today. Obviously, to find the mass, every item has a mass. So if you have a triple beam balance, you can find the mass by measuring it, okay? So we can also find the volume if it's a regularly shaped object, like my book or my domino, right? If not, we can use our water displacement idea. So regularly shaped objects have their formula, but those irregularly shaped ones, we can use water displacement. And again, this is showing this a little bit better. Here we have 20 milliliters originally. We drop the marble in, and the water level raises to 25. So my final volume is 25. My initial volume was 20. I subtract those, so the volume that was displaced was 5 milliliters. Well, the only thing that changed was I added that marble. So that means that the volume of the marble would have to be 5 milliliters. But is the marble a solid or a liquid? It's a solid. So can it use milliliters as its units? What would we have to change it to? Centimeters cubed. So underneath over here, I'm going to put liquids, and these are our solid units, right? All right, so we can use the graduated cylinder to find that volume if we're dealing with the liquid. So we can actually take measurements for mass and volume, which is great because those are our two variables for the density equation. So then we can just plug in mass divided by volume, and that would give us the density of whatever it is we are trying to find the density of. And so mass divided by volume, so for solids it's going to be the gram divided by the centimeter cubed usually, or gram divided by the milliliter if we're talking liquids. Okay, so remember yesterday how I said it's super important to realize if you're dealing with anything with the gram, boom, you're thinking mass. Anything with the liter, liquid volume. Anything with the cubed units, you're dealing with solid volume. So the units can be super powerful in helping you figure out what the numbers are if the wording is confusing or if it just seems a little bit like it doesn't come right out and say the mass is this or the volume is this. So those units can help you kind of decode. Okay, this is our first real hands-on practice with the equation. Again, we are gonna have, I don't even know, maybe 15, 20 equations total this year. This is the first time, so it's gonna go a little bit slower. It gets exciting because after we do this for 1 or 2 equations, by the time we've done it a couple times, you're gonna fly through. So it's fine if it takes us a little while to get the hang of it right now. We'll put in the hard work right now, and then it'll just be smooth sailing the rest of the year. So, if you're solving for density, you're just gonna use the equation of D equals M divided by V. And so sometimes you'll see these letters capitalized, sometimes they won't be capitalized. Those don't really matter. The only one that I care about capitalizing is that L for the units for the liter. All right, so don't let that throw you at all. Problem is, sometimes we're given the density and we're given maybe the volume and we have to solve for mass. Or maybe we're given the density and the mass and we have to solve for volume. So we can't always just use this equation, right? Sometimes we have to rearrange it. Sometimes it's gonna have to be set up to solve for mass. Sometimes it's gonna have to be rearranged to set up for volume. So this little triangle is gonna become very, very handy for that. As long as you know 2 of the variables, you can always solve for the 3rd unknown. And so this is something that is going to be true in all of our equations the whole year. Okay, are you still gonna come second? Okay, awesome, sounds good, thank you. Okay, and so in this little triangle, and sometimes it'll also be a circle, but you'll still have 3 variables. So you'll notice there's like these little division signs and then there's a multiplication sign. Anytime you're talking about something over something, that's like a fraction line, and fractions mean division. All right, so this is your number that's getting divided by this number. All right, and so we'll use that to help us set up what we're gonna do with these variables. Do we divide them or do we multiply? What do we do? So we're going to cover up the variable that we're solving for. And then the 2 variables that are left are going to basically tell you how to set up the equation that you're going to need. So, for example, the problem, let's say the word problem says, find the volume of an object that has a mass of 20 grams and a density of 2 grams per centimeter cubed. Well, all I would do is I'd cover up my volume, and I'm left with mass divided by density. So I would just rearrange that equation so that it's V equals M divided by V. So it's using that original equation, but it's just rearranging it. Okay, so pay close attention to the division and the multiplication signs, and then the pyramid will tell you how to set it up. Sorry. Okay? And we'll get lots of practice with this. So if you're like, wait, what? It'll make sense here shortly. Okay. So let's say again, you need to solve for volume. All you do is you cover it up, and on all your papers and on your test and everything, I'll always have this triangle. It will always be there for you. So it's not something that you're gonna have to draw on there or remember. It'll be on there for you. So if I cover it up, then I'm getting mass divided by density, all right? So the way this looks when you write it out is V equals M divided by D. And again, my little line here means divide, right? That's like our fraction line. So if you would need to solve for mass, works the same way. I still cover up mass, but now it's D times V. So I set it up like this. M equals D times V. So you don't need 3 separate equations. All you need is the one original density equation, and then using this triangle, we can rearrange. Make sense? It's pretty handy that way. All right, so here's some important things to consider. just like with every word problem, and like what we did with the half-life calculations, underline what's given and circle what you're solving for. Okay? You're gonna write your steps out as you work. I told you on the extended response part, the calculations for half-life on the test, if you show your work, I can give you partial credit. That helped a few people, because like they had the one answer wrong, but they showed their work and they had just done a simple math mistake. And so I was able to give them partial credit because I could see what they had done. They did the steps right, they just made a stupid calculation error. All right, but the steps and how they set it up were right. You always have to include your units, and always be careful. If it's a solid, then you're going to have your length units cubed, or that centimeter cubed, meter cubed, whatever it may be. Okay. The only time that's really a factor is if you're dealing with the water displacement idea, because it's probably giving you the volume in liters, and then you'd have to change it to the cubed unit. Okay. But in a word problem, you're not gonna have to worry about changing it. It's just gonna do what it's gonna do. It's just gonna stay the same. And so remember, anytime you see a liquid, you're gonna have some version of the liter. Anytime it's solid, you're gonna have something that's cubed. Okay? All right. Let's stop, because I don't want to. We will end with our song. Let's do that. Oh, yes. Don't you know me? Maybe we'll start.